Okay, hello everyone. So this is a last minute announced Zoom class. Sorry about this mishap. So I would like to move to public key cryptography. Explain a little bit about number theoretic problems that we are going to use in a public key cryptography, and we'll see how far we get in the applications. But the first applications will be key exchange and public key encryption. Okay, and there are related and sort of different points made on slides. So please have a look. In particular, there's something called very cute thing called Merkle puzzles, which is one way to implement key exchange. It's not particularly efficient, but it's kind of surprising that you can do that at all. So in some sense, you do that using just symmetric key crypto. And it uses this trick that is sort of comes up in security applications in other contexts. In many contexts, it's called a puzzle. So you can turn a cipher into a puzzle, and that's a cute thing that you can get from these slides. Okay, so let's start with groups and discrete logarithms. So we'll use modular arithmetics. So a modular function can be thought as a function. You take all integers and you output integers mod n. And what is integers mod n? It's a set of integers that result from modular residues of n, which is these integers. There's n of them. So these are residues of integer division by n, right? So in a group of integers, I can add, subtract, multiply, but when I divide, I go out of this set of integers, right? I cannot divide 3 by 2, but I can in the following way. So 3 by 2 is a quotient 1. So I find one entity of 2 inside of the 3 and a remainder 1. So these are residues or remainders of integer division. Okay. So Zn plus is a group whose elements are in the set Zn. Yes. An operation is an addition mod n. What's the addition mod n? So a plus b mod n is the okay, so it's this function. Okay, so okay, I guess I should define the function. So a mod n is a unique remainder R, such that two things happen. First of all, R is in Zn, so he's in this set. Secondly, there exists a quotient, which is also an integer, quotient such that A can be expressed as Q times N plus R. And this R is unique, right? So this is the quotient, and this is the remainder. So this is how integer division works, right? Like if I divide A by N, I get some quotient, and I get a remainder. And modular reduction is just asking what's the remainder, and I don't care about the quotient. What does it mean that it's a group? It means that, so what is a group? It means that if I add, I get an element from the same set. If for whatever values I have, if I perform the operation, I stay in the same set. Okay, that's one property. Another is that there are inverses. For every A in the N, there exists a B in the N, such that A plus B is 0. Well, this operation is a modular division, modular addition. Sorry. Yeah. So what is B? Take B, which is equal to N minus A. Right. For every A in this region, if you take N minus A, it's still in this region. And the two of them will sum to 0. Because they will sum to N over integers, but N is just 1 times N plus 0. So the remainder is 0. And yeah, okay. So that's is there some other property? No. I think that's it. Okay. Okay. But also you can define the following thing: Zn star is all those elements of Zn such that greatest common divisor of N and A is 1. So for example, Z5 star is, well, Z5 is 0, 1, 2, 3, 4. But greatest common divisor of 0 and something is 0. So it's not this. All the other 1, 2, 3, 4 are co-prime to 5, right? They don't have any factors with 5. So they stay in. But if you, for example, look at the 6 star, that has much less. It's just these two. Because who else is in the 6, right? It's a 2, but 2 is not co-prime with 6. 3, not co-prime. 4, not co-prime. 5 is. Yeah. So the 8, for example, will just not have any even number, right? But all the odds remain. Okay, etc. Zn star, it's also a group if operation is modular multiplication. So you can see that if AB are Zn star, so let's say they're here, N is 8, then A times B mod n, this new element, I take these two and apply the group operation, he's also in Zn star. because, well, this is definitely some integer, right? Because these guys are integers. Is it in the right range? Well, it's mod n, so it's in this range. So the only question is the GCD of this result 1 with n? But that's a basically question. Does this thing have any co-prime factors? Any common factors with n? Well, these guys didn't have because they were here. So, and to be here, you cannot have common factors with the modulus, right? So, for example, if the modulus is 8, you don't have a factor 2. And if I multiply these guys, I don't create any common factors with this modulus doing so, right? So the only thing is like, well, but then you take a modular reduction. So maybe you created a common factor. No, you haven't. So it's not easy, not hard to see that if this didn't have any common factors with n, and then you took a modular reduction, you cannot create because of this relationship. If there was some common factor with n here, well, there is a common factor with n here, so this guy would have to have a common factor with n as well, but he doesn't. Okay, you can do a multiplication table. In fact, that will be homework exercise when I will give you, some modulus, and say, okay, look at how multiplication works modulo that modulus. Just see, that, for example, you always stay within the same set. Because that's how the cryptography works for them. So it's nice to sort of practice this a little bit. Also, for every A in Zn star, there exists a B in Zn star such that A times B is 1. And this is a mod n, because the group operation was addition mod n. So here is also mod n multiplication. This is an identity in an additive group, and this is an identity in a multiplicative group. That's another group law, that like there is this identity element. So if you take any element and add this one, you get the same element back. But that's a triviality, right? Same here. For every A, if I multiply it by 1, I get A back. Okay. But this is a more interesting thing, that for every coin, there is another one, that if I multiply to 2, I get 1. So, okay. For example, for this group, okay, so 1 is its own inverse. 1 times 1 is 1. What about 5? Well, its inverse is definitely not 1, because 5 times 1 is 5, so I don't get that. But 25, 5 times 5, what is it mod 6? Well, actually it's 1, right? Because 25 is 24, 4 times 6 plus 1. So the remainder is 1. So far so good. But actually it's always true. Like, whatever modulus is, if you take numbers that are coprime with it, there's always this property that take whatever number, there is always some other one here, that if you multiply that one with these two, you get a 1. Okay. Okay. Oh, wait, you know what? It's hold on a second. Now I'm confusing myself. I think it's not true about this group, is it? Okay, 3 times 3 is 9, all right. 49 is 48 plus 1, okay. But what about 5? So, oh yeah, 25, yeah, okay. So just squaring them always gives you a unity. Yeah, okay, so it is true about that one, okay. Okay. Okay, what next can we do with this stuff? So, because multiplication is well defined in these groups, so what about so we can also exponentiate. So if some element G in a group, so take a group as Z and star for some n. So you have a modulus. This defines set of residues, and you only take those residues which are coprime with the modulus. Okay. Then G to the I, or let's say G to the X, is defined as G times G times G X times, right? Where all of these are group operations, and these groups are associative, so it doesn't matter in which order you perform the operations. In other words, are you just taking this element and multiplying it by G, and then multiplying it by another G, or perhaps you're multiplying from both ends, and then in the middle you're multiplying the result of this and the result of that. But it doesn't matter because they're associative. So this is, of course, defined if x is a well, it's a natural number, right? So I still don't know what exactly would mean, if x was 1/2, but for any integer, I can it just tells me how many times I should multiply g. Okay. So modular exponentiation can be implemented fast. How so? So an algorithm that takes G, a modulus, an X, and output G to the X mod n. And we assume that G is in Z and star, and X is a positive integer, so a natural number. Okay, that can be 0, but that's kind of trivial. I just output 1, right? X like this can be done recursively. Recursive code can be like that. If X is 0, return 1, right? So G to the 0 is always 1. Otherwise, let Z, let's say, be result of exponentiation of G n and X. Okay. Then let Q be you take a division of X by 2. Okay, and remainder be X mod 2. So recall that X is 2Q plus R, right? Because I exactly do the integer division. I take X divided by 2 and floor, and I take a remainder of this integer division by 2. Okay. Let Z be computed recursively like this, Gn Q. Sorry, this is not a great notation, but this is my new exponent. And output y, which is z square times g to the r mod n. Now, note, so this is g to the r is mod 2. So r is either 0 or 1. So this is simply z square mod n if r is 0, or z square times g mod n if r is 1. Yes, because r is just the last bit of x. So it's either 0 or 1. You can check that this. Okay. So let's check that this recursive code works. So let's say that the recursive call is correct, right? If z is indeed g to the q, then z square times gr is what? It's g to the q twice g to the r. So this is g to the 2q plus r. So this is g to the x. Yes. And the fact that it's a modular multiplication, that doesn't matter, because modular multiplication is just perform all the multiplications over integers and then take a modular reduction. So if it's true over integers, then it's also true in a modular arithmetics with arbitrary modulus, because it's just true over integers. Okay, so good. So this recursive call, if it's correct, then the output is correct. Okay. Now in a base case, so this is the recursive case, right? And the recursive case is correct. Like if you have the recursive call correct, then you're gonna output correct out. And what's else to check? The base case, right? So, well, what's the base case? If x is 0, then g to the x is indeed g to the 0 and it's 1, and then so the base case is done correctly too. And it really doesn't matter whether it's modular or not. Okay. Okay. Why is it fast? So the time of the X algorithm on GNX is what? Okay, well, I say this model, so this is just a check of the last bit of X, okay? So it takes like no time. The floor, it just means that you shift the bits, right? Like whatever bits were describing X, how do you compute this? It's the same bit, but with the least significant bit kicked out, right? Like just think of X in a binary. Yeah, you just kicked out the most significant bit, that's the least significant bit, that's all. So these operations take essentially no time. So the time of this is the time of X, G, N, and Q, which is this, plus what do you do? Okay, one mold, and then another mold. So you either have a single mold here, multiplication, or two. So it's up to 2 multiplications. Yeah, so this is the step where you actually perform some computation. You have to do a modular multiplication. But so recursively, if this guy had, let's say, k bits, then how many bits does this guy have? Okay, you have to speak up because there's no way you can like not know how many bits that thing has. How many bits does this have? Oh, half the bits? No.
K minus 1.
K minus 1. Yes. Right? Because you divide by 2, so you reduce the number of bits by 1. And so time of X on k-bit exponent is upper bounded by basically every time you do the recursion, you have 2 molds and you reduce the size of the exponent by a bit. So if you start with the k-bit exponent, it's k times is 2k molds. Yes. So this is efficient because the time of a modular mold, well, if the modulus is very large, it's actually not so, you know, the easiest algorithm would be square of the size, right? Because you take and you cross multiply everything. But it's actually, surprisingly, it's well, it's definitely upper bounded by okay, it's the length, the bitwise length of n to 1.7. So trivial algorithm is takes the length of the number to the square. Where I did, but this, my notation is a number of bits in n. Okay, so by length, I mean by length in binary. So it's a very cute algorithm if you've never seen it, that takes n-bit numbers and cross multiplies them in a time that is actually beats the quadratic bound. It's not hard actually, but kind of surprising if you've never seen it. So the end result is that time of exponentiation is the length of on the order of length of the exponent times length of the modulus to 1.7. And basically, these numbers are very large. So think of them as 1,000 bits, 2,000 bits. That's how it's gonna scale. It's gonna scale like the length of the modulus is 1,000, 2,000. So it's going to scale not linearly, but less than quadratically. And then additional factor is the length of the exponent. This formula basically kind of tells you also that public key cryptography, is going to be slower to implement than block ciphers and everything that we have seen earlier in the class. Okay. So, but okay, but like still, modular exponentiation can be done in some decent time. Okay. So why we care about modular exponentiation so much? Modular exponentiation will be like a public key operation. Okay, but like right now, it's very, very hazy, like what exactly it means. But let's introduce like the first type of cryptographic problem in this sphere, or it's called the discrete logarithm assumption. Holds for large enough primes, prime moduli. And they have to have special form. These prime moduli is not so material. Like the book has more, how exactly these primes should be chosen. But we'll skip many of these technicalities. The book actually has, it's a good source for them. The discrete logarithm assumption is as follows. The exponentiation function, and I'm going to be denote this function as index by Gn. It's a function that takes, I can think of this as a function that takes z, I'm going to take zp and output elements in z and star. Now, what is p? Where p is defined as the order of g in z and star. Okay, so what the hell is order of an element in star? Now this is defined as the smallest integer say x or I, such that g to the I is 1. Oh, smaller integer I, but it cannot be triggered. It cannot be 0. So it's a positive integer, such that g to the I is 1 modulo n. I told you that if you look at these modular arithmetic groups, like take a modulus and restrict yourself to all the numbers that are coprime with this modulus. You can multiply these numbers, and for each of them there is an inverse. So there is some other number that multiply with this one gives you a 1. And now we talked about exponentiation. So if you fix what, let's say this is your base g, you can think of like, what's the g times its set? Okay, well, it's some guy here. Then you can multiply that thing with a g. Yeah, that will be another guy here. And then once again by a g, and g, let's take one of them. Okay, assume g is 3. What this says is that eventually you will always hit 1. So after you multiply and multiply, you're gonna hit a 1. Why is that exactly? Okay, this is it's a Fermat's theorem actually, that for a prime modulus n, and actually no, for all moduli, if g is in Cn star, then there is always going to be an integer such that take g to that power and you hit a 1. Okay, so this, it's actually better. I will just give you some exercise forms like this. Like take some modulus, look at integers, and multiply them. And just see, okay, you always hit a 1. And it's kind of interesting also, like how long does it take to hit a 1? There are certain patterns in the length of such cycles, and they will be important because basically like short cycles are no good for cryptography because like space is too small, like you always hit the same thing eventually too fast. You want G's that generate a large, who have the large order, meaning you can exponentiate them with large integers and still you don't hit a 1, but eventually you will have to. If this is an order, so basically this function is defined as exp gn of x is g to the x mod n. Okay, so well defined, right? This is in Cn star because g was in Cn star, and once you multiply any Cn star elements, you remain in Cn star. So this is all good. This is definitely in Cn star if g is in Cn star. Okay. Exp gn function is efficiently computable. That's the last slide, right? That's what we argued with this recursive algorithm. This recursive algorithm, by the way, is called square and multiply. Let me write this down here. This recursive code is called square and multiply algorithm. Yeah, and that's because you're just squaring. As you make recursive calls, you always, on the way out, you square the result. And sometimes you just square and that's it. And sometimes you multiply with a base. And whether you just square or square and multiply is just based on the bit of x, which you process at that point in the recursive call. So you just take your exponents, you read off the bits, and this basically tells you, are you just squaring or squaring and multiplying? And that's it. It's very easy to code in a loop. Okay. Why am I restricting the inputs to the P, where P is the order of G? Makes sense because if G to the P is 1 mod n, and it is because P is defined as the order, so P does have this property, the G to the P is a 1. Then G to the X mod n is equal to the Gx mod P mod n. In other words, for all integers, integers x. So you see, this integer is clearly in ZP, right? Because ZP is just a set of residues mod P. Okay, this is an arbitrary integer. But an exponentiation of G to an arbitrary integer, I don't have to perform it. I first look at the arbitrary integer and reduce it mod P. And I only perform exponentiation on the result of this modular reduction. That's why it's only, exponentiation is not interesting to look at like what happens in some other places, because you take the integer in some other space and you reduce it to this space. Why is that? Well, why? Okay, so if x mod P is the remainder, then x is quotient times P plus the remainder for some Q. Right? If I look at what is x mod P, it's a remainder of integer division of x divided by P. So think of some quotient here, right? And this equation is true for some integer quotient. And then see that if you wanted to compute that, well, x is this thing. So x is q times p plus r. Well, so I can take it as x q times p times q times r. And what is this? Well, I can look at this as g to the p to the q, and I repeat this. And this thing, by our assumption, is a 1. So this is 1 to the q times g to the r. So this is g to the r. So this thing is the same as this thing. Yeah, all these multiplications were mod n. Yeah, so some of these work over integers, but like, for example, this one didn't work over integers, right? Over integers, g to the q is g to the p is some huge number, but mod n, g to the p is the 1. It's yeah. So that's why basically if p is like a length of the cycle, if you look at g and you multiply by itself, by the time you do it p times, you're coming back to unity. If you do it one more time, you're coming back to g. One more time and it's g squared, and then it's g cubed. And then if you do it 2p times, then you're back to unity. So these are cycles. You go from g to g squared to g cubed, dot, 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 dot. And by the time you reach g to the p, that seems that actually is a 1. So you do it one more time and you're here, and you're going to circle forever. That's why if you take g to however big integer, it's not really important how big, where this integer is. What's important is where is this integer in this cycle? Where this is a 0, this is a 1, this is a 2, 3, okay? And then the one before that is g to the p minus 1, right? So if you do a modular reduction, you're somewhere here from 0 to p minus 1. That's the range, possible range, right? Okay. Okay, we're still not yet at what's the discrete logarithm assumption. Okay, so we talked about this. This is an efficient function, and this is the restriction of the input makes sense. Okay. What about the inverse of this function? What about this a function which is an inverse of that one? In other words, it goes from here and it outputs something in ZP which inverts this. No one knows how to compute that fast in general. So for some moduli, there's some trapdoors. Some moduli are basically bad. There is some special structure that allows you to compute discrete logarithms. So this is a discrete logarithm because it's an inverse of an exponentiation, just like standard logarithm is an inverse of an exponentiation. The discrete logarithm function base g modulus n takes values in here. Okay, you know, this is actually I have to modify this, and that, well, so this is definitely the range of this function, but it's not necessarily the image. In other words, there's some elements here that might not be. If you perform this map, perhaps you're gonna miss some of them. So all these guys, they sit somewhere in Zn star, but it doesn't mean that they form the whole Zn star. Let Gn stand for a set like this: g to the 0, g to the 1, g to the 2, da 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 da, g to the p, where p is the order of g in Zn star. This is called group or subgroup generated by g in Zn star. And this will be homework. I will give you, like, okay, some modulus, some numbers, and identify what subgroup this, you know, what subset a fixed base generates. Does it generate all moduli? When you just look at these kind of products, g squared, g cubed, g fourth, and so forth, do you are you actually going to cover all of these moduli? For some choices of g, no. For some choices, yes. For some, it depends on. You will see. Okay, so let's let's redefine exp as a function that just has this range. So it's some subset of Z star, but it's the same function. X Gn of x is g to the x mod n. Let discrete logarithm based Gn be an inverse function. So it takes all of any element in this subgroup and outputs a value like this, such that it's an inverse. So such that discrete logarithm of value y equals x, if and only if g to the x is equal to y mod n, i.e. This discrete logarithm function is an inverse of the exponentiation function. Yeah, because the exponentiation went forward, like right on an argument x, it gave me this y, which was exponentiation of g to the to exponent x. But now I want to compute backwards. I get an y, and I want to find this exponent x such that this is true. So pictorially, here is Zp, all the remainers mod p, and here is this subgroup, which is some subset of C star, which is generated, which looks like this. It powers, oh sorry, it's powers of G. Yeah. Perhaps it's the whole C star. Perhaps it's all the moduli here. All the residues can be described as powers of G. Think that at first. There is a function here that is efficiently computable. It's this exponentiation function. And there is a function well defined, the discrete logarithm function, that takes any element here and goes back. Oh, well, I never said that this exponentiation function, once defined like this, it doesn't collide. So there cannot be two moduli, x and x prime, such that g to the x is equal to g to x prime. But that's the reason, not because this p was the smallest element that satisfied it. If you found x and x prime which collided, that means that the cycle was shorter than it was supposed to be. So it's just visible from here. Like, g to the x and g to the x prime cannot equal if x and x prime are just residues mod p. Or if they were, then this cycle would be far shorter. Discrete logarithm assumption . So the short story is that this is easy to compute. But this is hard to compute. The discrete logarithm assumption so exactly in what sense is it hard? Is that for every efficient, and this assumption is on this group, or really a family, because it's asymptotic, so you have to basically define like certain class of integers on which this would work, and this class has to be defined for every security parameter, or otherwise you have no asymptotics. But that's kind of technicalities. Okay. So we will just get completely bogged down if we try to spell them all out. For every efficient algorithm A, the probability that A given a Y outputs X, where Y is chosen at random in this range, and X is defined as discrete logarithm of Y.
The paper up.
Yeah, is negligible. Okay, so they basically that's what it means that computing this function is hard. Any efficient algorithm that is given random, so computing this function, the exponentiation function is easy. If you get a discrete this logarithm exponent, you can compute this forward, right? Because this is the square and multiply algorithm. You could take g to whatever power and compute this. But if the opposite direction, somebody gives you a random number here and asks you what is the exponent, such that exponent x, such that g to that exponent x gives you this number. So an attacker, and also he gets to see, he also knows the g and he knows the n. So he knows the parameters, he knows the base of the group, he knows the modulus. He can also know this p, okay? All of these are public parameters. But his goal is to invert this function to compute discrete logarithm. And this is the basis of a lot of crypto systems. But we'll have to postpone, of course, the rest till next week. I'll post reading guides where you can start reading the stuff, playing with modular arithmetics. I understand that most of you will be busy with and prioritize the homework from the symmetric crypto segment, but that's okay. So we'll just slowly move with this stuff, and whenever you read up on it, you will start understanding, get a better feel for the stuff. Okay, I will stop recording.